Magniez. I'm going to share this session. So it's a quantum session. So today we'll have, so I just make a very short presentation and then we start with the talks. We have 5 talks. I underline the name of the speakers. So we'll have a presentation on new algorithm, but also new limitation, and as well as a new result on the model of computing itself. So what's interesting, I think, is that in particular, most of this result establish and use a new connection to classical complexity theory. So the first talk considers the difficulty of classical simulation of quantum circuits. So this question is really hard, and this paper proves new hardness results for a specific type of classical simulations. So the second talk will be on the other side, namely, it establishes the limitations of some quantum heuristics for hard classical problems. And those heuristics are very well adapted for near-term quantum device, but this paper shows their limitations. So the third talk will address a fundamental paradigm of quantum circuits. So using intermediate measurement is a way to reduce the number of qubits, but on the other hand, it is crucial to avoid intermediate measurements for many algorithmic purposes, such as quantum amplification, for instance. So surprisingly, this paper provides a simple compromise using a fresh study of pseudorandom generator in the quantum settings. So fourth talk, we consider the study of noisy quantum circuits, and in particular, how to control their errors. So it is known how to control the total error of any circuit when each gate introduces an error below some threshold, but this comes at the price of some space and time overhead. And this paper establishes in particular some new result on the space overhead. And the last talk will consider the potential of quantum computing in a distributing setting. So there have been recent development in this area suggesting that the impact of quantum computing is both underestimate and not well understood for distributed computing. And this paper provides new results based on new tools. So it's a large set of topics we cover today. So I stop sharing my screen. And Shir, you can start sharing your screen. So you have 9 minutes. I may send a small notice when there is 1 minute left.
Okay, you can see the screen? You can see the slides? Yes, okay, great. So hello, my name is Shir Peleg, and this is a talk about lower bounds on stabilizer rank. This is based on a joint work with Amir, Shpilka, and Volk. So we'll start with the following settings. So we have a Boolean function f from f2 to the n to the complex field. And we want to express f as a linear combination of base functions, where our base functions are -1 to the power of a quadratic polynomial over f2 to the n. So these representations are sort of a generalization of the Fourier representation, because if we only allow linear functions in the power, this would be exactly the Fourier representation of f. Now we have a larger set of generators that we're interested in. And there is an amazing fact. So we have this magic function, we call f of h, we call it the magic function, which is, as I defined here, on the point x, it outputs sine of pi over h times the Hamming weight of x, times 8 to the Hamming weight of x, times cosine of pi over h to the power of n minus the Hamming weight of x. And if we can express this magic function f of h using a linear combination of polynomially many functions of the form -1 to the q, then p equals np. So I think this fact is quite amazing when it's stated like that. And the reason it's true is even makes it even more amazing. And the reason is that if it's true, we can efficiently simulate BQP and even post-BQP using classical computer. And this is true due to the Gottesman-Knill theorem. So if this is true, we can simulate efficiently every efficient quantum circuit. And the actual result allows more general class of functions as their base function, and it allows us, motivates the definition of a stabilizer rank of a Boolean function, which is denoted by chi of f. And it's the minimal R such that we can choose R affine subspaces, R quadratic polynomials, and R linear polynomials, such that f can be represented as the following linear combination. So for every choice of an linear polynomial, quadratic, and an affine subspace, we take I to the power of the linear polynomial times -1 to the power of the quadratic polynomials times the indicator function of the affine subspace. And for every choice of linear function, quadratic polynomial, and affine subspace, this product is called a stabilizer function. And the stabilizer rank of the function f is the minimal R such that f can be represented as a linear combination of R stabilizer functions, any R stabilizer function. Okay? And the stabilizer function, the connection to quantum computation, so they correspond to quantum states that are called stabilizer states, which are states that are generated using Clifford gates, for anyone who knows. And the fact is that we can classically simulate any efficient quantum computation using time which is polynomial in the stabilizer rank of the magic function that I presented before, f of h, fh. So this is why this is correlated to simulation of quantum computers. And let me take a few minutes and go over some known results. So before our work, the best lower bound for the stabilizer rank of our magic function was square root of n due to BSS in 2016. And there is an upper bound, a non-trivial upper bound of 2 to the alpha n, where alpha is log of 3/4 due to QPG in 2021. And this is the last of a long line of work that proving this kind of result for smaller and smaller alphas, values of alpha. And as I mentioned before, the stabilizer rank of the magic function is super polynomial unless p equals np. So this is due to HNS in 2020. When we assume the exponential time hypothesis, then the stabilizer rank of the magic function is indeed exponential. And this is due to MT in 2020 and again HNS in 2020. And if we, so as I mentioned before, the stabilizer rank of a function is the minimal number of summons in a linear representation of stabilizer functions that generate the function. So if in the linear combination we only allow small coefficients, then the measure is indeed exponential. And this is again due to BSS 2016 and BG in 2016 as well. And in this work, we gave a lower bound of linear lower bound for the stabilizer rank of the magic function. And we also showed a lower bound of square root of n over log n for approximations of the stabilizer functions. That by that we mean that any approximation in L2 norm that is close to our function up to some constant delta, small constant delta, also has large stabilizer rank. And yes, so this problem is also correlated to a problem in analysis of Boolean function called the quadratic uncertainty principle. So in this question, we eliminate the affine subspace and the linear functions, and we only consider function of the form -1 to the q, where q is quadratic. And we ask how many summons must be in the linear representation of the end function. And the conjecture is that you need exponentially many summons. And so the best known lower bound for this conjecture is n over 2. And it is still open to prove a superlinear lower bound for any explicit function. So any explicit Boolean function, there are no better than linear lower bounds. The best that we know is that Williams in 2018 gave so a function in NP. For every k, he gave a function in NP that needs at least n to the k summons in the representation, in this kind of representation. So this is correlated, but it is less general than the stabilizer rank model, as indeed the stabilizer rank of the end function is 1. So when we allow the affine subspace, we can just pinpoint 1 point and get exactly the end function. So this is similar, but less general than the stabilizer function. And I won't go into the details of the proof here, but you are more than welcome to watch the full video. But I'll go over the open problems that we mentioned. So of course, improving the lower bounds for the stabilizer rank, there are 2 follow-up work to our works due to Labiv and Lovitz-Stefan, and they use different techniques, but prove the same lower bounds. And again, improve the lower bounds for the quadratic uncertainty principle. And we believe that these 2 problems, our technique made us think that these 2 problems are somewhat correlated. So maybe improving one should help you improve the other, or the ideas should be similar. So thank you for listening, and I hope you enjoyed.
Thanks a lot. Is there any question in the audience? Can eventually write it in the chat if it's easier.
What?
No, I mean, if someone has a question, you can write it. Please.
Yeah. Sorry, just had a quick question. I didn't fully follow how the stabilizer rank related to the Gottesman-Knill theorem. Like the function f, what exactly are you decomposing? Like, is it? So
the function, if you know, I didn't mention it because I didn't have time, but the function f
is fine.
If the function is a representation of a Boolean function as the nth tensor of the H state, or the magic state of H, which is what you get by applying the 0 state to the T state, if you know the T state. So, and Knill says that you can simulate Clifford circuits. So if you if you can replace the H gates, H states with some small linear combination of Clifford states, then you can simulate any circuit.
Thank you.
You're welcome.
Sorry, I have another question.
Yeah, so we have to move on. So maybe very quick question.
Yeah, so my question was, if we just look at representing functions as linear combinations of the indicators of affine spaces, then is it easy to prove a lower bound on the number of such indicators needed for any explicit function?
Yeah, I think it should be easier, but I don't have any function in mind. I think it should be maybe majority should be maybe the majority function should require a lot of, but I'm not confident enough to.
Okay.
Yeah.
Okay.
So thank you.
Thanks a lot. So you can stop sharing your screen. Kunal, is you have the token. Good. You can start. Your mute on. You should unmute.
Okay, can you hear me okay? Shoot. So hi there, my name is Kunal. I'm presenting a work from last June on algorithmic limitations for maximum cut on high-girth graphs. This is joint with Boaz Barak. So I'll give a brief overview of the problem. I'll talk about the state of the art for max cut and give a brief discussion of the main technique. And you can watch a longer version in the video. So what is the maximum cut problem? just for completeness sake, if you take a graph and you want to split it into two parts and you want to maximize the number of edges between partitions. This problem is NP hard, so most people study approximation algorithms. There's a very popular algorithm called the semi-definite programming algorithm, or using a semi-definite relaxation. It's a classical algorithm, but it's not local. And I'm going to be interested in local algorithms, primarily comparing classical local algorithms and quantum local algorithms. And so what do I mean by local? Let's call an algorithm local with respect to some graph if every vertex is labeled with from some IID distribution, and then you recompute the label using only the radius k neighborhood in the graph. So at small k, you can't see the whole graph. So it's kind of like a limited model of computation. You can think of factors by ID algorithms, but also there's a variant of this where you can think of quantum computation as being local. And the thought is, how powerful are these local algorithms? Are there anything you can say about maybe the limitations of these local algorithms? The reason I bring up local algorithms for quantum computation is because there's these noisy intermediate scale quantum devices, or these NISQ devices that people talk about. I would say you'll see them through the next decade. And every operation you run on a quantum device a quantum computer is noisy. So there's only so many operations you can run before the noise overwhelms the signal. And so one way to model this is kind of with low depth circuits, or kind of, let's call them local quantum algorithms, where you can't actually have a circuit depth that's too large. And so one question is, are these NISQ devices, which we have for the next decade or so, are they useful for anything? And one real question is, are they useful for combinatorial optimization? And there's a popular algorithm style called the QAOA that's kind of been making rounds in industry and in national labs, but there's not a ton of theoretical evidence to show that it's useful or not useful. And so one way to model this is kind of with a graphic that we're calling NISQ optimization advantage. So I'll take a little time to explain this figure. The green line is this any quantum local algorithm that's like one step, like the locality is depth 1. And the yellow line is any locality at constant depth. And the black line is any classical algorithm. And so across all CSP instances, are there any CSP instances, any instances of problems where quantum local algorithms at constant depth are somehow achieving higher values than classical algorithms? And so this yellow crossing the black line, we don't know if this happens. If this happens, this is like a lot of theoretical evidence to suggest that quantum computers of today are useful for combinatorial optimization. So I'll talk a little bit about what's going on with maximum cut. It's a very commonly studied problem. It's an old problem. Instead of looking at the approximation ratio, I'm looking at a different metric. The metric I'm looking at is cut fraction. So approximation ratio is like the percent of optimal you can get on a particular graph. Instead, I'm just taking high girth or random graphs and trying to see how many edges can I cut. So the maximum amount of edges you can cut as n and d grow large on a random graph is half the edges plus some constant over square root d. And there's a connection to statistical physics, which c is, the best c you can get is like 0.76. It's related to the Parisi value, a particular spin glass problem. So I'm plotting on this plot the value of c. And it turned out there was a time when the QAOA at the lowest depth was the most powerful algorithm on this metric. It achieved like 0.31 or something. And it was a little confusing. Is the QAOA the best algorithm we have? It's a local algorithm. It's a depth 1. That seems really surprising. So it turns out the answer is no. Maybe obviously, but the answer is no. And there is a classical algorithm that is also one local that achieves slightly higher cut fraction in expectation. And so you might say, is this true at higher depth? And it turns out, so I did some work last year that the answer is no again for 2. And I should mention that this QAOA is relatively challenging to analyze at high depth, which is what makes the theory limited. So in this work, amongst other things, the most exciting thing I think in this work is we were able to show a bound on all one local algorithms, whether they're quantum or classical. any algorithm that is limited in its information cannot achieve higher than 0.71. So it's a non-trivial bound. It's not, it's not really tight, but it is a non-trivial bound. And the technique is, I think, completely new, where you're going to use correlations of random walks and use that to bound kind of like the expected cut fraction you can get, or the chance you're actually going to cut an edge on a random graph. So this is kind of a cool new technique that could be valuable in other settings, or maybe again on maximum cut. So I'll give an overview of the main technique. I'll just talk very briefly about it. So the theorem that we have is like you have a high-girth graph and you have a one local algorithm. Could be quantum, could be classical. And the maximum expected cut fraction you can have is half plus c over square root d, where c is bounded. So how do we get this bound? So I told you I'm looking at correlations of random walks. So when you take a random walk, s steps, you're going to end up some distance away from where you started. And when you can calculate the chance of how far away you go. So when you're distance 1 away, this value, the correlation of distance 1, it's related to the maximum cut. Because if the two labels are related, if the two labels are the same, then they're going to end up in the same partition. So the edge will not be cut. And if the two labels are different, then the edge will be cut and they'll be in different partitions. So this distance 1 thing is really is related to the value of the CSP that we're looking at, the cut fraction. But if you go beyond the light cone of this local algorithm, so beyond 2K, there's going to be zero correlation. And so there's a tension between walking too far and you have zero correlation, and walking very close, and that's actually the value you're looking for. So we're able to kind of cleverly construct a random walk to bound the correlation between adjacent labels. And this bound, this square root 2 over d, becomes, you can relate it to this constant. And so one question is, like, can you generalize this technique in other problems or at higher depth? And we weren't able to do that. I think it's totally possible that it could be done. But for the story we have here, the real question is, do quantum local algorithms, are they effective on maximum cut? And it turns out actually in November, asymptotically, the answer is no. Like, classical algorithms achieve optimal performance on maximum cut on random graphs through a recent paper with Montanari. But it might be possible that there's no combinatorial optimization problem, that quantum local algorithms are useful. And so one really important thing is, I think, theoretically, is to kind of either say yes or no. Should we be spending so much money on quantum computing for combinatorial optimization when there's no evidence to support it? In fact, it might be like a waste of funds and we could use the money somewhere else. So thanks. I'll take any questions. And I'm actually at U Chicago now. I'm a PhD student there. And so you can write to me or talk to me. Thanks.
Thank you. We have time for one question. Maybe stop sharing your screen. Yeah. Okay.
This meeting is being recorded.
Okay, so maybe we move to the next talk. Omar, can you share your screen, please?
Sure.
There's a question by Sevag, maybe.
Sure, I can answer that briefly. So in November, there's a paper, I'll just link the paper in the chat, that for maximum cut on random graphs, as the random graph gets very large, both n and d get large, there is a approximate message passing algorithm that achieves optimal. So,
thank you.
This race that we've been doing, trying to compare quantum and classical algorithms, at least on random graphs, the race to me is over. Classical algorithms are able to achieve it. Now that, there still may be other CSPs where quantum local algorithms are valuable, but it's not clear what.
Thank you. So Uma, can you unmute and share your screen, please? Perfect, you can start.
Okay. So I'll be talking about eliminating intermediate measurements using pseudorandom generators. This is a joint work with Ras. So here are our results. Our first result is that we show a way to differ intermediate measurements for quantum algorithms in a space-efficient and time-efficient way. More precisely, for time t spaces algorithms, we show that you can eliminate intermediate measurements in time t poly s and space s log t. Our second result is that we study pseudorandom generators for quantum algorithms that can read classical random bits. We show that a variant of the Impagliaso-Nissan-Wigderson generator fools such algorithms. So now let me describe these results in more detail. So first, what is a quantum algorithm of space S and time t? So there are a lot of intricacies involved in defining such algorithms, but for this talk, for the sake of simplicity, just think of a quantum algorithm as a quantum circuit. So space S and time t corresponds to having S qubits and applying t operators. What kind of operators are allowed? This is a really important question, and based on the kind of operators we allow, we could get potentially different models of computation. So on the one hand, we have the unitary model. So fix any set of gates that is universal for quantum computation, unitary gates, for example, the Hadamard and the Toffoli gate, and look at circuits that are built using these gates. This gives rise to the unitary model of quantum computation. On the other hand, you have the unital model, where you can perform measurements during computation. So measurements are not unitary operators, and typically we only allow measurements to be performed at the end of the computation. But in this model, you're allowed to perform measurements during computation. This is what we call the unital model. Note that in this model, you can store measurement outcomes by copying the measurement outcome onto a fresh qubit, but you will have to pay in terms of the space required. So this qubit is going to count towards the space. So you can store measurement outcomes, but you'll have to pay for the space to store these measurement outcomes. So given these two models, the big question here is this: are these two models different? Given a quantum algorithm with intermediate measurements, can we simulate it by a quantum algorithm without intermediate measurements? Do intermediate measurements give power to quantum computation? This is a really fundamental question in quantum computing. This also has connections to reversibility of computation. So this question is asking, can we simulate the irreversible operation of a measurement by doing reversible operations in an efficient way? So what do we know about this question? One very basic principle in quantum computing is the principle of deferred measurements. This says that instead of measuring a qubit, you can copy that qubit onto a fresh qubit and ignore that fresh qubit for the rest of the computation. This implies that to defer measurements for time t spaces algorithms, you can do it in time t and space s plus t. So why is there a space s plus t? Because the original algorithm could perform up to t measurements, and to defer each of these measurements, you need a fresh qubit. Note that often it is the case that s is much smaller than s is much smaller than t. So for example, think of the setting when s is polylog t, then the space blows up from s to s plus t. So this is an exponential blow-up in space. So one can ask, is there a version of the principle of deferred measurements that is space efficient? Can we defer intermediate measurements in a space efficient manner? This was an open question until last year. It was resolved by these two works independently, that indeed you can defer measurements in a space efficient way. So for time t spaces algorithms, you can defer intermediate measurements in space s plus log t and time polynomial in t and 2 to the s. Typically s is at least log t, so the overhead in space is constant. However, the overhead in time in this simulation is really large. So think of the setting when s is much larger than log t. In this case, you have a runtime of 2 to the s, which is quasi-polynomial overhead. So with regards to eliminating intermediate measurements, the best known ways to eliminate intermediate measurements required either time 2 to the s or space t. this is the issue that we address in our work. So we show a way to differ intermediate measurements in a space-efficient and time-efficient manner. So we show that to differ measurements for time t spaces algorithms, you can do it in time t poly s and space s log t. In other words, we give a version of the principle of deferred measurements that is both space-efficient and time-efficient simultaneously. So this result, for example, implies that quantum algorithms of polylogarithmic space and polynomial time don't require intermediate measurements. So this is our first result. Let me now describe our second result and also the connection between our first result and the second result. The connection is in the following powerful observation. Intermediate measurements and randomness are equivalent. First, intermediate measurements can be used to generate randomness. So take a qubit in the state 0, apply a Hadamard and measure it. The measurement outcome is going to be a uniformly random bit. And to generate more random bits, you'd again and over apply the Hadamard and the measurement gates. Interestingly, the other direction also holds, that is, randomness can be used to simulate intermediate measurements. So we show that instead of measuring a qubit, you can equivalently apply a controlled unitary on that qubit, where the control is on a uniformly random bit. Thus, intermediate measurements and randomness are equivalent. The proof of this is a simple calculation. Let's see how it is used. So by what I just said, given any quantum algorithm with intermediate measurements, you can write down an equivalent quantum algorithm without intermediate measurements, but with access to uniformly random bits. Therefore, the problem of eliminating intermediate measurements is equivalent to the problem of removing random bits, or in other words, the problem of de-randomization. The idea is then to replace these uniformly random bits by pseudo-random bits. So these are bits which contain very few bits of true uniform randomness, and the rest of the bits are actually a function of these few random bits. This leads us naturally to the concept of a pseudo-random generator. So let me briefly describe what a pseudo-random generator is. It's basically a function that stretches a very few random bits to a large number of random bits. And the property we want of this function is the following. In the ideal case, you have an algorithm of space S time t. You're giving it a uniformly random string over a large universe, and you're looking at the output. On the other hand, you have this algorithm F. You're taking a few random bits, stretching it using the generator, and then feeding it to the algorithm. The property we want out of a PRG is that the behavior of this algorithm in these two different situations is close, is nearly identical. So we want to simulate the behavior of the algorithm on a large number of random bits by using a few random bits and stretching it using the pseudo-random generator. So now I'm ready to state our second main result. We study the Impagliason-Nissan-Wigderson generator. This is a famous classical generator for time t spaces classical algorithms. We show that a variant of this generator actually works for quantum algorithms of spaces time t that read classical random bits. So to the best of our knowledge, this is the first such result of its kind. Quantum PRGs for quantum algorithms that read classical random bits is something people have not studied a lot before, because presumably quantum algorithms can generate perfect randomness. But this relies on their ability to perform intermediate measurements. So we think in situations when the quantum algorithm cannot perform intermediate measurements, or it cannot be relied upon to do what it's supposed to do, we think that PRGs might find applications in these settings. So this brings me to the end of my talk. Let me just put up the slide to summarize what I've said. So any questions?
Good.
In analogy to the sort of conjectured improvements to INW in the classical space-bounded case, could we hope to eventually get a simulation with like order S space rather than S log t?
Sorry, what is the conjecture regarding the classical?
Oh, I'm just in the classical setting, INW has a seed of it's like quadratically worse than what we would hope for if you have a log space algorithm. And so in the quantum case, is there an equivalent hope to improve our space overhead by a quadratic? I guess I'm thinking of S as log t, but by going down from S log t to just S.
Yeah, so this really relies on the kind of pseudorandom generators we use. So in the INW case, you have this recursive construction built on the extractor property. And here we are able to use a quantum extractor to have that kind of property. So I think it would really depend on the kind of generator that you use. We don't see a black box way to translate PRGs from classical to quantum, but depending on the kind of extractors or what kind of objects are used, it's possible that they do.
Thanks.
You also have, I guess, a simple question in the chat. Do you read it? Or?
Let me.
Can you see it, or I can read it?
Is the classical randomness read in by the classical Turing machine that generates a description of the circuit? So no, we require that the Turing machine that generates a description of the circuit is deterministic. So it's deterministic log space. So the randomness is only for the circuit. Only the circuit takes in the randomness. I hope that answers the question. And there is another question: how do your results compare with Pfefferman Rebscrim? So this is a good question. So in this talk, I've said all the operators are unitary measurements and unitary gates and measurements. But this Pfefferman and Rebscrim, they consider a model where you're also allowed to reset a qubit. So this is in some sense taking a qubit in an arbitrary state and mapping it to the 0 state. And they show that even such kind of operations can be removed in this same overhead in space and time. So their result is stronger than our result. However, if you look at the setting when, so that still requires a 2 to the S overhead. So even to eliminate intermediate measurements, you require a 2 to the S overhead in time. So to the best of our knowledge, our results are, this new work is kind of incomparable to that because we get a better runtime dependence, but our space is S times log t instead of S plus log t. So it's in some sense incomparable.
Thank you. So it's time to move to the to the next talk. Ala, can you unmute and share your screen, please?
Okay. Can you see my screen?
Not yet. Yeah. You are not in full screen, but that's okay. It's perfect. You can start.
Hi, everyone. So I'm going to talk about a joint work with Omar Fawzi and Alexander Müller-Hermes on space overhead of fault-tolerant quantum computation. So one of the fundamental results in theory of quantum computation is the fault-tolerant threshold theorem, which states that you can do arbitrarily long computations on a noisy quantum computer as long as the noise level in your quantum computer is below a constant level, which is known as the threshold value. And indeed, you can achieve fault tolerance with a very reasonable overhead in space and time. So there exists a fault tolerance scheme which, given a circuit of depth n, depth c, and width n, outputs a fault tolerant circuit of depth t prime and width n prime with only a polylogarithmic overhead in n and t. And here we define the space overhead as the ratio n prime over n, and time overhead is defined as t prime over t. So more recently, Gottesman showed that assuming good quantum error correcting code exists, then satisfying certain properties exist, then you can achieve constant overhead fault tolerance asymptotically. And more recently, Fawzi et al. Proved that quantum expander codes actually satisfy these desired properties. And they actually showed that you can indeed achieve a constant space overhead. However, unlike the threshold theorem, which applies to arbitrarily long quantum circuits, the proposed scheme only applies to circuits that have depth at most polynomial in the width. And this motivated us to think about the following question. So given a noise model, how does the necessary overhead to achieve fault tolerance grow as a function of the circuit size? So in recent years, a lot of effort has been devoted to introducing new recipes for fault tolerance. But study of fundamental limitations of fault-tolerant quantum computation has received far less attention. And this is partly because it's really difficult to provide a definition for fault-tolerant quantum computation in the first place, in order to be able to actually talk about properties, like general properties or limitations of fault-tolerant schemes. So I've listed some relevant results on limitations of noisy quantum circuits. These are very interesting results, but they have some limitations. For example, most of these works assume classical computation is also noisy. And we know that today we can do classical computation with practically perfect accuracy. So this is not a realistic assumption. And in fact, the limitations shown in these works fail to hold even if we assume that classical computation is noiseless, even for arbitrarily long circuits. Most of these results only apply to circuits under strong noise, and in particular, noise levels beyond the threshold value. The circuit models considered in these papers are sometimes restrictive. So the circuit, like the gate set, is sometimes limited. The output of the circuit is assumed to be obtained by measuring, for example, the constant number of qubits, or fresh ancillary qubits are not available during the computation. And finally, in most of these works, only depolarizing noise is studied. So in this work, we prove a lower bound on the space overhead of fault-tolerant quantum computation, and we try to address these limitations. So before stating our result, I need to define our model. So a quantum circuit in our model is an ordered sequence of quantum channels, or completely positive and trace-preserving linear maps, acting on a potentially non-trivial input system. And so in our model, we distinguish between classical and quantum subsystems. And so the number of qubits may vary in different time steps. So we can introduce fresh ancillary qubits or measure qubits. Now, for the noise model, we consider IID noise, where in each time step, every qubit is subject to some noise channel N. And we allow classical computation to be free and noiseless. And since in our model, we allow arbitrary quantum gates, unitary noise is not really an interesting noise model because it can be perfectly canceled in each time step by the gates. So we focus on non-unitary noise. Okay, so our main result is the following. Let N be a non-unitary qubit channel. Then for any fault-tolerant scheme against IID noise modeled by the noise channel N, the number of physical qubits is at least the maximum of the following two bounds. The first bound is alpha n times lag t, where alpha n is a constant depending only on the channel N. And the second bound is the inverse of the quantum capacity of the noise channel times N, where the quantum capacity is the maximum rate at which you can transmit quantum information reliably over the channel. So in order to prove this theorem, we first need to define what we mean by a fault-tolerant scheme. And in this work, we consider a very natural and simple fault-tolerance model with minimal assumptions. And in our model, a fault-tolerant scheme is a circuit encoding map associated with a family of quantum error correcting codes. And we only require fault-tolerant scheme to be able to implement arbitrary logical circuits on encoded data. In other words, we allow the encoding of the input state and the decoding of the output state to be perfect. So our second bound in terms of the quantum capacity is actually a direct consequence of our model of fault tolerance. So it's easy to show. So next I'm going to explain how we prove the first bound, and let's give you some idea. So we consider circuits of the following form of width n and depth t, in which in every time step, the registers are partitioned into A and B subsystems, and the circuit is only allowed to act locally on the A and B parts and communicate only classically between the two parts of the circuit. So intuitively, such a circuit shouldn't be able to preserve entanglement between the two parts for arbitrarily long time. And our contribution is actually a quantitative version of this statement. And in particular, we show that the amount of entanglement decays by a factor of 1 minus p to the n in every time step, where p is a constant depending only on the noise channel n. And here we quantify entanglement using the chi-squared divergence from the set of separable states. And in case you're not familiar with this, it's not really important. It's just a measure we use to quantify entanglement. And using this lemma, we can obtain an exponential upper bound on the maximal length of computation against amplitude damping noise. And this actually resolves an open question by Ben-Or et al. From 2013. And okay, let me finish by some open questions. So of course, we can try to improve our lower bounds. In our model, we allow gates to act simultaneously on all the qubits, but in reality, we are always restricted to act locally and on a limited number of qubits. So it would be interesting to see how like geometric locality restrictions affect the space overhead of fault-tolerant computation. And it would be also interesting to study IID noise modeled by channels in higher dimensions. Thanks. I think that's all I wanted to say.
Thank you. So maybe one quick question. Okay, so in fact we are running out of time, so good, thank you. So it's time to move to the last talk. Can you unshare? Yeah, Dean, can you unmute and share your screen, please?
Yes. Okay, can you see my screen?
Not yet. Yes, it's okay now, you can start.
Okay, great. Thanks for the introduction. And so yeah, this is work on quantum distributed algorithms for detection of cliques. And it's joint work with Karen, Orff, and Swan wrote that. And basically we asked the question, well, when we have lots of quantum computers and they all have to talk to one another, how can we detect cliques faster? Okay, so the problem that we tackle is subgraph existence. These types of problems are very common in distributed computing and also in sequential computing. And they say the following: we have some large input graph and we have some small subgraph, for example, a triangle. And we're tasked with doing one of three things: either detecting, saying if the small subgraph exists anywhere in the input graph; counting, which is giving an exact number of the number of times the subgraph exists in the input graph; or listing, where listing is the most challenging version. And we're tasked with finding every single instance of the subgraph in the input graph. In the distributed setting, each one of these problems has its own definition. For example, for the listing setting, we have that every node in the graph is some computation unit, and every computation unit outputs some list of the instances of the subgraph that it sees. And it has to be that all the lists put together is exactly the list of all the instances of the subgraph and the input graph. And so that's a problem that we try to solve. So what do we do in this paper? Our main result is showing how we can take algorithms for listing cliques of a certain size, for example, some size P, and then using nested Grover searches, nested quantum Grover searches, in order to detect cliques of larger sizes. The way that we do that is we introduce a new distributed framework for using these nested quantum searches. And it's the first time, as far as we're aware, that quantum searches are nested into one another in the distributed setting. And we also do this in a way such that it doesn't require any quantum knowledge whatsoever. We provide some black box, and now any distributed researcher can go ahead and use this black box in order to develop new algorithms. So just as a taste of the results that we show, we, for example, take a known algorithm for listing all triangles in n to the 1/3 rounds, and this is a classical algorithm, and we turn it into an algorithm for detecting if there's a clique of size 4 in the same round complexity. In general, this is the result that we get. The blue line shows the runtime for listing cliques of a certain size in the non-quantum setting, in the classical setting. And the red line shows how long it takes us to detect the same clique size using quantum computation. And so as we said for triangles, we're able to detect if there's a triangle in n to the 1/5, where classically finding all triangles takes n to the 1/3. And so forth, we go ahead and we show this for any general size P, for any size clique. Interestingly, the blue line is also lower bound in the quantum setting. Listing cliques in the quantum distributed setting takes the runtime of the blue line, and we basically show here a separation for cliques of all sizes. So that means that in the quantum distributed setting that we work, detecting if there's a clique of a certain size is faster than listing. This was unknown. So we show this for all cliques, except for size 3. For size 3 was known in previous work, which was also co-authored by the session chair. And so this separation is very interesting because in the classical setting, this is unknown. We don't know if this currently holds in the classical setting, except for triangles, which is known in the classical setting. For cliques of size 4 and above, this separation exists in the quantum setting and not in the classical as far as we know. So we'll start with just a small taste of how we do this. And you can see the rest of the talk recording if you want to see more. So just a small, how do we do this trick? How do we go from listing cliques of size P to, for example, detecting cliques of size P + 1? So Grover search is a well-known quantum algorithm, which was developed many years ago, and basically says if we have some array and we know that one of the values is 1 in the array, then we can find this index in square root of n time, where n is the length of the array. More generally, it says that we have some function f, and we can feed it some input. And if it's a Boolean function and there is some value that outputs 1, then we can find some x star in square root of the size of the input domain time. It was also recently shown how to do this in the distributed setting. In the distributed setting, we have some graph of nodes which communicate with one another. And we select some leader node. We give this leader node some input x. And in order to evaluate the function on x, the input node, the leader node, together with the other nodes, communicate for some C number of computation rounds. And after C rounds, the leader node knows f of x. So this is how we evaluate a distributed function. Now, if we do this with quantum computation, then we can say that the leader node can perform the distributed Grover search locally, where every time we need to query the function, it communicates with its neighbors. And so using Grover search in the distributed setting takes C rounds, where C is the number of times to check a single input, times the square root of the input domain size. What we show with this, for example, we take an algorithm which performs listing of cliques. For example, listing of cliques of size 4 would ensure that every single clique of size 4 is known to some node in the graph. For example, this orange clique will be known to the purple node. So we run some known classical algorithm for listing cliques of size 4. Then we go ahead and we show that if we want to check for a single specific node, does this node extend some clique of size 4 to a clique of size 5? We show that if its neighbors broadcast to the entire graph that they neighbor this node, then it's possible in O of 1 rounds to detect if this node extends some known clique to a clique of larger size. Since we have to check this for every single node, and we can run a Grover search on this, and we have n nodes, it takes square root of n number of rounds in order to check if there's some node in the graph which can extend a given clique of size p to a clique of size p + 1. And so what we get here is that if we want to detect clicks of size p plus 1, the runtime that it takes is the same runtime as listing all clicks of size p, and add square root of n rounds to that. And so already here we show a separation for all clicks of all sizes, for detecting clicks of all sizes. We go ahead and we extend this to nesting the Grover searches, which basically means we take the same algorithm here, and we note that we had some classical setup here. And then we did some classical checking algorithm, and we ran some quantum search over this classical checking algorithm. Basically, what we go ahead and we now do is we say, what if we replace the checking algorithm, and instead of using a classical one, we use a quantum checking algorithm. And this is where we get nested Grover searches. So we perform some classical setup time, and then we perform some Grover search. And then inside the checking procedure, we perform again some classical checkup time, and then another quantum Grover search. And the reason, and this speeds up our detection even faster. And the reason that it works is because it's based on some nice distributed trick, where the trick is that in the distributed setting, we pay just for communication between the nodes. And so when a node learns some information classically on one step, in the future distributed checks, with the Grover searches, it can reuse this information without having to pay for it again. Basically, what we get is that we show the following result, that we can extend click listing for size p by any t that we want. And so and as the click size grows larger, it becomes worth extending more. Finally, we go ahead and we say, well, we had all this was with any black box listing algorithm. We didn't assume anything on the listing algorithm itself. We go ahead and we open this black box and we create a tailor-made specific quantum listing algorithm that works together with our quantum searches. And this makes us even faster. And so just a final result that we show, we also show that it's based on some of the work that we show here and some results from recent papers. We show that it's difficult to show lower bounds for detecting clicks in the quantum distributed setting because it would imply results in circuit complexity. So to summarize, we show how to extend classical algorithms which list clicks of a certain size to those in the quantum setting which detect clicks of larger sizes. In order to do it even faster, we open up the black box and create a specific tailor-made quantum listing algorithm that works even faster with our detection algorithms. And we also attach onto this some results that we show for hardness of showing lower bounds in the setting.
Thank you. So there is time for one question. Yes, so Martin?
Yeah, thanks. It ties a bit into the slide before the summary. How specific are your results to cliques? So what about detecting other substructures?
Okay, so this is also a general question for the distributed settings. So currently, most of the results are cliques and cycles, where those are most of the results that are currently known. Where the big difference between them is that in the distributed setting, you really, as the information is more local, you can run much faster typically. And for detecting clicks, because every single node has to be connected to one another, it really helps. For detecting cycles, for example, you get into problems because you have to learn information that's not directly known to one of your neighbors, for example. And so that becomes even more complicated. But most of the results are around clicks and cycles. Our results are specifically for clicks. We also have some results on cycles, but they're not some, there are some adaptations of the existing cycle detection algorithms. And they weren't in this paper though.
Thank you. So if there is no more question. So this concludes the session. So thanks to everyone, thanks to the authors. So we have a break and then there is a session for graduating bits. See you later. Bye-bye.